We're now going to turn our attention to what is known as limiting reactant stoichiometry problems. And limiting reactant stoichiometry problems kind of fall in an analogy of what happens when you're trying to bake a cake, but you don't have enough eggs for the flour and the sugar that you have on hand. You run out of eggs, and you cannot continue making cakes if you run out of an ingredient. Well, the same idea applies in chemical reactions. If you run out of a reactant, don't have enough of it to completely react with the other substances that are reactants in the process, then the reaction will come to a stop. The reactant that runs out first is known as the limiting reactant. So the limiting reactant, and we're going to use this term so much that I'm going to abbreviate it L period R period, is the reactant that is used up or runs out first in a chemical reaction. As soon as you run out of any reactant, the reaction has to come to a stop. You can't make any more product. Just like if you run out of an ingredient needed to make a cake, can't continue to go on making cakes. Therefore, the limiting reactant limits or sets a cap on how much product can be made. That's where we come up with the term limiting. It's a cap setter. It limits or puts a cap on how much product can be made, and also on how much of excess reactant or reactants, more than one, is left over. Notice when you're doing limiting reactant problems, or you must show a comparison to determine which reactant is the limiting reactant. Now, this information is found in Chem 2A in Chapter 7 in Section 7.9 and in Chem 22 in Chapter 8, Section 8.6. So how do you recognize that you're even looking at a limiting reactant problem? Your signal that the problem is limiting reactant is that you are provided quantities of 2 or more reactants. As soon as you see that you are given quantities of more than one reactant, you have to ask yourself, I wonder which one is limiting. I wonder which one is going to run out first, and therefore the reaction stops and you can't make any more product. So you're provided quantities of 2 or more reactants, and you must calculate by showing a comparison which reactant is used up first. How do you do the comparison? The comparison is done by calculating the amount of the same product that can be made by each of the reactants, assuming that it can react completely. The limiting reactant makes the smaller amount, so I'm underlining that and stressing that, the smaller amount of product. The reaction must stop at this point because you have run out of the limiting reactant. It's all used up, none of it is there. Notice this smaller amount of product made is called the theoretical yield for the reaction because it is actually what you are able to, it is what you are predicted to make from the calculation. You can't go on and make any more. You have to stop with this theoretical yield of product. However, when you go into the laboratory, what you can actually obtain in the laboratory may be different from even the theoretical yield, and we'll talk about that in the next segment. So the smaller amount of product made from the calculation is referred to the theoretical yield of the product because it's calculated from the stoichiometry setup. Here's an example to help illustrate these ideas. If 56 grams of sodium metal reacts with 69 grams of chlorine gas, question 1, what is the limiting reactant? Which one of these reactants, sodium or chlorine, is going to run out first and cause the reaction to stop? Number 2, what is the theoretical yield of our product? And notice the product is going to have to be sodium chloride. That is the only thing that we could make from sodium and chlorine reacting. And number 3, how much excess reactant remains in grams? So you recall that in order to do any stoichiometry problem, we have to have a balanced equation. Our reactants are sodium metal and chlorine gas, and as the problem implies, we are making the product sodium chloride, which is a solid at room temperature, as all ionic compounds are. Now the equation needs to be balanced. You cannot do a stoichiometry problem without a balanced equation. You need those coefficients to get the mole to mole ratios. And looking here, I see that I have 2 chlorine atoms as a reactant, so I'm going to need to put a 2 here, and let's maybe make that a little less crowded. I'm going to put a 2 here in front of the sodium chloride as a product, and now I'm going to put a 2 here in front of the sodium, and let's make that pop a little brighter using blue. A 2 here in front of the sodium to balance this equation. So I'm looking and I see that my equation is balanced. Now I have to show a comparison to determine the limiting reactant. So what am I going to do? I'm going to calculate how much of the product sodium chloride can be made from each one. And again, you're always comparing the amount of the same product. So how much sodium chloride can I make from the 56 grams of sodium? And then I'm going to do a second calculation asking how much sodium chloride can be made from the chlorine gas. So I have indicated the quantities of each reactant under their formula. This is another quick signal that I am looking at a limiting reactant problem. So, how much sodium chloride can I make from the 56 grams of sodium metal? Just ignoring chlorine for a minute. That is a simple stoichiometry problem, standard stoichiometry problem, as we looked at in the previous video clip. So I'm going to take this mass of sodium. I'm going to remember that flow chart. I take my mass of given substance and I convert to moles of given substance using the molar mass of sodium. So I'm going to need my periodic table here, and I see on the periodic table that 1 mole of sodium has a molar mass of 23.00 grams of sodium. And I'm being careful with my significant figures, 4 sig figs in the initial data, so I'm using my molar mass to 4 sig figs. If I stop my problem right now, I just calculated moles of sodium, but I don't want to know about moles of sodium. That's a given substance. I want to know how many grams of sodium chloride can be made from the sodium. So how many grams can you make from the sodium? And I want to compare that to how many grams you can make from the chlorine. Which one makes the smaller amount? So I need a mole-to-mole ratio from the balanced equation to calculate how many moles of sodium chloride can be made. And I see here that it is 2 moles of sodium chloride that is produced for every 2 moles of sodium metal that react. So if I stop my problem right now, I just calculated how many moles of sodium chloride I could make from the 56 grams of sodium, right? But I'm asked to calculate the amount of sodium chloride in grams. So I'm going to have to do that last step, and I'm going to have to use the molar mass of sodium chloride, adding up 1 mole of sodium with 1 mole of chlorine. And when I do that on the calculator, so adding these numbers up on the calculator, I get 58.45 grams of sodium chloride for every 1 mole of sodium chloride. In other words, This is the molar mass of sodium chloride I'm using in the problem. And now we're just going to plug and chug through the setup, plugging in all of these numbers, operating on them with our calculator. And I see here that I am coming up with a value of 142.3 grams of sodium chloride. And it's a very good idea when you are taking a quiz or an exam to run through that calculation a second time. I'm not going to do that right now because I already did it before we started together, and I came up with this value the first time I did it, and we have confirmation here that I didn't make a calculator error plugging in the data. Important to check that. Now, if you stop right here, you're assuming that you have plenty of chlorine to react with the sodium, but maybe you don't. Maybe chlorine is in fact the limiting reactant. Maybe the chlorine gas runs out first and you cannot make 142 grams of sodium chloride because you run out of chlorine gas before you can make it. So we have to show a comparison. We have to do this exact same calculation, forgetting about the sodium now, assuming that we only have chlorine present, and calculate how much sodium chloride can be made from the 69 grams of chlorine gas. So same process. We're taking our mass of chlorine and we're converting to moles of chlorine using the molar mass. Chlorine is a diatomic element, so I'm going to have to add up the masses of 2 moles or 2 atoms of chlorine to get that molar mass. And when I do that calculation, I come up with 70.91 grams of chlorine per every 1 mole of diatomic chlorine, taking the molar mass of chlorine and multiplying by 2. Now comes the heart of the stoichiometry problem, that mole-to-mole relationship from the balanced equation. And I see that it is 2 to 1, that I am making 2 moles of sodium chloride for every 1 mole of chlorine that reacts. So here is the heart of the stoichiometry problem, this mole-to-mole relationship from the balanced equation. But I need to go on and not stop here. I see that if I stopped, my grams of chlorine are canceling, my moles of chlorine are canceling. I'm left with moles of sodium chloride, but I need to take it to grams of sodium chloride to make the comparison. So I'm going to use that same molar mass of sodium chloride, 58.45 grams of sodium chloride per every 1 mole of sodium chloride, and do the plug and chug, plug in the numbers into my calculator, crank through the answer, and when I do this calculation, I come up with, and hopefully you are calculating right along with me, I come up with 113.8 grams of sodium chloride that can be made from the chlorine. So I am ready to make a comparison. Which one of these reactants is the limiting reactant? The limiting reactant will make the smaller amount of product, and my eye sees immediately that the smaller amount of product is the 113.8 grams of sodium chloride. So this is the amount that will be theoretically made in this reaction. We haven't actually done it in the lab. This is just a calculation on paper, so theoretical amount made, right? 113.8 grams of sodium chloride. We cannot make any more sodium chloride at this point because we run out of chlorine. So chlorine is the limiting reactant. This is the reactant that runs out first, producing 113.8 grams of sodium chloride, which is our theoretical yield. So we have an answer to the first question. Chlorine is the limiting reactant. We have an answer to the second question. What is our theoretical yield? It is 113.8 grams of sodium chloride. Now the only question that remains is how much of the excess reactant is left? Well, looking here, I can see that sodium must be present in excess. We have to have leftover sodium if we run out of chlorine gas first. And how do I figure out how much excess sodium is remaining? Well, let's kind of find a little corner here to do this calculation. And I'm going to erase right here and try to squeeze in this calculation right in this new spot that I have opened up on the board. Once you know what the limiting reactant is, it is in what I call the driver's seat. It is determining how much product can be made and how much of all of the other reactants are used up. And we need to find out how much sodium is used up before we can find out how much is left over. So I'm going to take my 69 grams of chlorine. So we're calculating here right now how much sodium reacts with the 69 grams of chlorine. We have to find out how much reacts to figure out how much is left over. Again, we can do a stoichiometry calculation to answer this question. 69 grams of chlorine gas, converting to moles of chlorine. 1 mole of chlorine, we have that molar mass conveniently right there from our calculation here. So 70.91 grams of chlorine per 1 mole of chlorine. If I stop my answer right now, I just calculated how many moles of chlorine I have, but I'm wanting to get to sodium. So looking at the balanced equation, I see that 2 moles of sodium react with 1 mole of chlorine. So right here, straightening that line out a little bit, right here is the heart of the stoichiometry problem, that mole-to-mole relationship from the balanced equation. 2 moles of sodium react with every 1 mole of chlorine. If I stop my answer right now, I just calculated how many moles of sodium reacts, but now I need to take it to grams because I need to calculate my answer in grams. So using that molar mass of sodium from the periodic table, it's also right here, 23 grams of sodium per every 1 mole of sodium. My moles of sodium cancel. And if I stop this calculation, I will find how many grams of sodium reacted with, was used up, reacting with the 69 grams of chlorine. So taking my calculator and doing that plug and chug process, plugging in the numbers, and then calculating how much sodium metal reacts, right? When I do this calculation and I'm quickly clearing and doing it one more time here to make sure I didn't make an error, I come up with the same number twice. I get 44.76 grams of sodium that reacts. That means it's used up, right? But we were asked to calculate how much of the sodium, which is excess, remains. So this can't be the answer. This is how much sodium metal reacts or is used up. Well, how much sodium did we have to begin with? We had 56.00 grams of sodium to start with. And hopefully you see right away where we're going with this calculation. If we had 56 grams of sodium to start and we use up 44.76 grams, then the amount of sodium metal that is remaining has to be the difference between those two numbers. So 56 minus 44.76, I am calculating 11.24 grams of sodium is left over. In other words, it's in excess. So I have 11.24 grams of sodium metal, my excess reactant, left over.